This lesson is about the application of FTIR spectroscopy, so infrared spectroscopy or Fourier transform infrared spectroscopy, using the ATR probe. ATR stands for Attenuated Total Reflectance. There are different kinds of probe that we can use and set up for infrared spectroscopy. For our application analysis of the parchment and the iron Gall ink, ATR FTIR spectroscopy is very suited, so we will see the application of this specific method. For this lesson, we are going to examine the parchment, the antiphonary parchment that also I have on my back. So this is the front, and this is one side, this is the other side. And also we are going to test a modern, contemporary, recently produced parchment. Before we move into FTIR examination, I want to discuss the structure of the parchment. In particular, we need to be able to distinguish the air side and the flesh side of the parchment. Air side is basically where there are the hair on the skin. So we are going to see the follicles, the structure of the skin, upper part of the skin, and then the flesh part is the one on the flesh that will be, of course, more smooth. In this lesson, we also covering the coatings over here, coatings. This means all those material that could be on the manuscripts that are related or to conservation procedures or could be related to the manufacturing process of the specific parchment. And also we will discuss how we can identify, if we can identify iron Gall ink using FTIR. This is the equipment we will use for the FTIR spectroscopy. So this is a handheld FTIR system, where basically from here you can change the kind of probe. So right now the probe mounted over here is an ATR diamond cell, with a diamond cell on top of it. So the acquisition, so on my back is the software for acquisition. So what we see here is a live view acquisition, a preview of the spectrum. Okay, so basically, since when we do ATR, the contact with the object is very important, should be very intimate. It's good to have this preview so we can check if you are positioning the probe right angle in particular. So this one is a modern parchment. So we put the instrument in contact, so we can hold like over here, so it should be in contact. We can put just on top of it, and on the spectrum you see over on my back, depending how we tilt it a little bit, we can get a better spectrum. You see, I'm just tilting in one direction or the other. Okay, once I can find the better position, I can start the acquisition. So I click over here and the system is collecting the measurement. And there it is. So we got our spectrum of the parchment. Let's discuss it. This is the spectrum we just acquired for a modern contemporary parchment. So this is the typical spectrum. What we see over here basically is this main absorption band. The first one over here is the primary amide, then it's followed by the secondary amide over here, and then we have this group over here, the tertiary amide. So this is the typical spectrum of the collagen, and parchment is made mostly of collagen. So we are moving now to measure the actual parchment that we have in our lab, and we start with this side, that is the hair side. So the spectra that we see actually over here that we collected You see, this one red is the parchment from the antifonari, so the old object, and this one is the modern parchment that just measured in the slide before. So we see that they overlap, and this is normal, what we expect for two parchment, where we are going to see basically the features of collagen again. No? So basically the primary amide, secondary amide, and tertiary amide, this big peak over here. Then I measured the other side of the parchment. This is the skin side. So we made the measurement, and surprisingly, the spectrum that we got is this one, the blue one. So you see this is the image of the actual this side of the parchment as a reference. So the blue one over here is the spectrum. So what we see is the spectrum, the sorbents bands, typical of calcium carbonate. So what happens? What we are seeing here is the coating on top of the collagen. Because remember, this is important property of ATR FTIR. Using this kind of probe, the ATR, the system is sensitive just to the very surface of the object. So we are talking about a few microns. So basically, what happens is that if on the collagen, on the parchment, there is a coating of calcium carbonate, a lime process that could be due to the manufacturing process or just to make the parchment more whitish or more suitable for writing, we are going to see just this material that is on the top. So don't be surprised if you, instead of collagen, you will see just calcium carbonate. And indeed, this calcium carbonate we saw when we did the analysis using the USB microscope. Let's look at that class, where you will see that we clearly see that there is a whitish coating on top of the parchment. Okay, now we move into the actual measurement of the iron Gall ink. So the black ink over here, we know that is iron Gall ink because it was already measured with Raman spectroscopy. So this is the spectrum that we get. Let's interpret it. On the bottom, we have the spectrum of gypsum as we have it on the pigment checker over here. So basically, gypsum is a calcium sulfate, and we see these two peaks. This main peak, sorbent spin peak over here, typical of the sulfate, and this other peak over here, typical also of the sulfate. So we see that in our iron Gall ink there is a lot of sulfate. This sulfate could have a different origin. We could consider, first of all, that iron Gall ink is made with iron sulfate, so it makes sense that there is a bit of it in the composition. In general, sulfates in inks are due to components in its manufacturing process. In this spectrum, we also see the peaks of oxalate, calcium oxalate. Oxalate are generally generated as a degradation products from tannins and from could be the gamma arabic. But they can be formed also by fungal degradation of carbonates. It's very common to find them in old samples, so where there is an ongoing degradation process, and oxalate are found everywhere, like paintings, sculptures, every basically object where there is some calcium carbonate. There would be also oxalate. In conclusion, basically we saw the main peaks that we detect with ATR FTIR on the iron Gall ink And this information, these peaks are not really specific of this ink. So definitely to identify the ink, it's much better to work with Raman spectroscopy, because there we have very specific peaks and a very specific way spectra to identify the object, the material. FTIR gives information on the parchment, on its manufacturing process, on materials that are on the surface of the parchment, and also could have information like gelatinization, and information on the degradation of the parchment itself.